She presented this.
Yes.
And actually, I helped review her. Yes, I helped her review the paper. So because I watched that presentation, I eliminate some of my contents because she introduced a lot of the NIMR basics.
Yeah. Awesome.
Yeah, I remember the work. Yes, I remember this group and I remember the work. Yes, yeah. She presented this. Yeah, actually, I helped review her. Yes, I helped her review the paper. So because I watched that presentation, I eliminate some of my contents because she introduced a lot of the NIMR basics.
So, guys, the transmission in YouTube has started. Thank you all for being here today, distant from each other but together at the same time. Dr. Zhang, thank you so much for joining us today, showing us and presenting your work. So Zhang is an assistant professor in the Department of Geology at the University of Kansas. She received her PhD in environmental geophysics from the Rutgers University in 2012. She research focuses on study complex fluid-rock interactions using geoelectrics, nuclear magnetic resonance, and modeling tools. She is interested in understanding the tightly coupled physical, chemical, and biological processes that govern the behavior of geological media and their constituents like water, brine, CO2, and hydrocarbons, from the micro to macro scale. Currently, she works on understanding water distribution, weathering, and geochemical fluxes in carbonate rocks. So, Dr. Chi, whenever you're ready, you can start. Thank you again.
Thank you, Ulisa, for introducing me. Thanks for Andreas for the warm invitation to invite me to give a talk in your wonderful Paleo Coffee Seminar series. So today, actually, I'm going to talk about how we use mostly NIMR technology, nuclear magnetic resonance, to probe the water distribution in carbonate rocks. And I want to provide a critical zone perspective to show you how we use this technique, also combining with other geophysical technique to look at the pore structure, the flow distribution, as well as the weathering pattern. So I just want to give a very quick overview about these two pictures here. So this is where I'm from, basically on the left, the Flint Hill, Kansas, which is a tall grass prairie, and it's also a dedicated long-term ecological research site. And it's a beautiful area and has the best scenery in the Midwest of US. And you see all this tall grass prairie, especially wonderful if you go there during the sunset time. And on the right, it's also related to the carbonate rocks, which is the limestone Alps. Oh, I forgot to mention, in the concept prairie on the left, we have a very interesting karst system called a merokarst system, which is a less developed karst system, has a featured with a single bedding of limestone, shale and limestone. But this kind of merokarst system is very well distributed and popular across the world. And on the right is the limestone Alps, probably some of the more familiar carbonate or karst features we're familiar with, such as the caves and sinkholes and so on. And to just give you another note about my personal background, and currently I'm in Kansas, but I'm gonna move to University of Vienna just next year. So give you a little bit of introduction about my overall research interest. So what I'm interested in, I'm basically interested in using geophysical tools to characterize the rock-fluid interaction with application to water and energy as well as the environment. So being in Kansas, we're facing a lot of this food, water, energy challenges, just like many other places. And my interest is really to look at how we use the geophysical sensing together with the theory and modeling to look at this physical property, geochemical reactions, as well as biological activities in the subsurface. And we're looking not just the architecture, meaning the lithology, the pore structure, we're also looking at the reactions, such as interfacial properties, the chemical reactions, as well as functions, such as groundwater flow, the fluxes of the water and CO2 and other nutrients, as well as evolution of the landscape, such as the secondary porosity development. And some of the examples of my application will be aquifer characterization using geophysical tools, and also catchment scale ecohydrology to look at how the groundwater, surface water interact and how the vegetation can impact this interaction, and also to monitor and track the solute and contaminant transport, and as well as some of this biomineralization application, especially at the lab scale, the column scale. And the last one is a weathering pattern, which is one of the research area I'm recently focusing on. So in terms of my research strategy, it means what kind of tools I use, how I link everything together. I just want to give you an overview of this. So basically, in terms of the scale, from the pore scale, we take the microcity image of the rocks and we do some of the imaging to review the 3D structure of a rock or sediment that we're interested in. And then we combine some of the modeling effort, which has the fluid and electric current simulation, as well as the Pore network modeling, and also coupled with geophysical responses, such as electrical modeling, electrical response, NIMR response simulation. And this is just one of the example, and the left figure showing that the microcity image. And then we combine with our lab experiments. And this lab experiment, the tools I'm mainly using are the complex conductivity and the nuclear magnetic resonance. And then we also scale up to the field. We're trying to extend the observation we get from the lab scale to the field scale to better understand the large scale phenomena and the processes. So in the field, we're basically using resistivity based tools, geoelectric based tools, as well as the NIMR tools. The NIMR tools we use in the field has both the borehole tools as well as the surface tools. So from this chart, you probably can see that my research actually goes from the pore scale to the field scale, and I'm trying to do my best at the different scales and trying to find out some of the fundamental problems, and also to link some of the important parameters across different scales. So why we're interested in the carbonate system? The carbonate system actually, if you look at this map in the middle, which is modified by this paper 2003, this one shows the global exposure of the carbonate on the Earth's surface. The carbonate rock is a major reservoir rock for the groundwater as well as for the oil and the gas. And about 20% of the ice-free terrestrial land is composed by the carbonate rocks. Although carbonate minerals do not create a net change in the atmospheric CO2 concentration over the long time period, but they can also affect the CO2 concentration at short time period, and they also in the local environments. Because of its fast responding to the perturbations like land uses change or the anthropogenic impact. So this carbonate system is very vulnerable and has this fast kinetics, and I think it's a very good challenge for us to study the carbonate system. So as I mentioned at the beginning, some of the karst system we're familiar with. For example, like the left one we're showing here, that's the world's largest sinkhole in China. It's called Xiaozhai Tiankeng, and this is the deepest and largest sinkhole. Or we can think about the carbonate system associated directly with the landscape or with the groundwater resources, like the one shown here. This is me on top of the Dachstein mountain in the limestone Alps. So with all of this importance, that's why it motivated me to study the carbonate critical zone. And I'm not sure if you're familiar with the critical zone idea. You probably heard about this word for some time. And just to reiterate the critical zone. This is the zone we call the skin of the earth, which extends from the unweathered rock to the canopy of the tree. And because of the zone is highly interacted with each other, between the different components, the physical, geological, and hydrological processes and interact at multiple spatial and time scale and create very complex ecosystem and functions. So to me, to study a critical zone, especially the carbonate critical zone, I think the most important thing, it can be divided into two categories. The first is to understand the architecture, meaning the lithology, the pore structure, and as well as the regolith depth. And then another category is to study the functions, such as water distribution, water, sediments, nutrients, and the carbon dioxide or carbon fluxes, and as well as weathering and the reaction to the perturbations. So because of this dominant process by the chemical weathering due to the dissolution and the reprecipitation, it has increased the variability of the fluxes, the water, sediments, as well as the nutrients. So to summarize my recent research questions, I think this fall basically outline my research interest. The first is the pore structure and the flow property. The second is the rock fluid interactions. And the third is water flux, storage, residence time. And then the fourth one is the weathering pattern rate. So today I'm going to mainly talk about the first question, R1, as well as a little bit of R3 and R4 using a case study. So let me introduce what kind of tools I'm using. So this is my secret weapon, the nuclear magnetic resonance in hydrogeophysics. So basically, I'm using the tools for all three types of NIMR, the lab NIMR, the borehole NIMR, as well as a surface NIMR. The underlying physics are very similar to each other, and just the way of the application is different. And I realized back in July, this seminar series featured another talk from one of the wonderful research groups within your own institution. And during that talk, the author gave a very good detailed background about the NIMR theory. So today I'm going to just quickly review the NIMR theory. So the NIMR theory is based on the response of the nuclei to the magnetic field. If you can imagine this, each of this individual hydrogen, the proton, they behave like a spinning mini bar magnets. And if we don't have a background magnetic field, and all of this magnetic moments of the nuclear spin are random. But if we put them into a background magnetic field, and they results in a net magnetization, and we call this M here. An NIMR experiment starts with placing this proton in a static magnetic field B non, and then we apply another secondary magnetic field under the radio frequency pulse, which is B1. And in this way, we move this proton's magnetization to another plane, and then we remove this secondary magnetic field, so this proton can relax back to the original status. And this time for this proton to relax back to the original status is called the relaxation time. And this relaxation time can be used to characterize the porous medium with various different pores. So for example, if you have a large pores, this relaxation time can be long. And if you have the small pores, relaxation time can be small. And very often in a natural geological medium, you will see multiple pore size coexist in the system. So that's why we have this multi-exponential decay. And using the inversion methods, we can invert this multi-exponential decay curve to the relaxation time distribution, and this we can correlate it with the pore size or the pore structure of the porous medium. And the NIMR measurement can be done in two ways, depending on the which of this plane you're looking at. We have the transverse relaxation time, more frequently used called T2 relaxation. We also have the longitudinal relaxation time, called T1 relaxation. And the T2 relaxation, T1 relaxation, they all associate with a bulk relaxation as well as a surface relaxation. However, the T2 relaxation is also subjected to the diffusion relaxation. And this BSD here denotes the bulk, fluid, surface induced, and the diffusion diffused relaxation time. So what do we do using these wonderful tools? So you probably can already guess. The first thing the NMR is sensitive to is the total amount of the proton, which means it can give us how much water you have in the system. Put into a geological background setting, we have the depositional fabrics, which means the salting grain size and also different type of grain, as well as the diagenic fabrics such as cementation process and compaction process. All of the process can alter a geological medium, and this alternation will result in the different size, a shape, or type of pore attributes, and also this results a different flow path, which means that you have a different heterogeneous distribution of the permeability. So this one, it's a figure generated by my PhD student, Fan. Sorry about this. This one, we give a general idea how we're trying to link everything together. So we combine with some of this petrographic information, such as the city image, the SEM image, and also the scene section, and with some of the petrophysical approach using the geophysical tools, such as complex connectivity and also NMR, and trying to look at the different pore attributes, and as well as to estimate the flow property like a hydraulic conductivity. And then we should have this in mind that we always wanted to upscale to the field applications such as well logging as well as the surface NMR. And here I'm showing an example of how we link this to the well logging data by looking at the one set of particular parameter T1, T2 ratio. I'm going to talk about this in detail later. So the challenges here is it's very difficult to build the robust and also mechanistic petrophysical relationships that beyond the empirical link to actually connect the observation from the geophysical signals to the actual property of interest. So this is something many of us been working on for all the time, and which is trying to build a robust and a universal petrophysical relationship. You can directly translate all of these geophysical signals to any of these properties you are interested in. So give you one of the example how we use the NMR to get the pore site distribution. So this is a actual sample we collected from Kansas carbonate oil reservoir, and which is from quite deep, around 4,000 feet. And this is the data collected by my PhD student Zhang. And on the left, you see the three types of different rocks, which are the greenstone, packstone, as well as the mudstone. And using this relationship, basically, if we assume this is a fast this is a fast diffusion regime, and we can attribute the T2 distribution only to the surface relaxation time, and therefore we got this equation here. And if we assume the pores are spherical, and we can get this relationship, which is the T2 relaxation time equals 3 times the radius of the pore, and divide by the surface relaxativity, ρ2, which is a constant. And if we determine this ρ2 independently from other methods, such as some kind of calibration using the BET on molecular intrusion, and you can see here we did exactly this procedure, and we used the BET to calibrate this ρ2 value. We got 2.8 micrometers per second for the greenstone, and 0.6 for the packstone, and 0.1 for the mudstone. And we use above equation, therefore we can calculate the pore size. So this is how we use NIMR signals to calculate the pore size distribution. And another one I want to mention along this line is, if we look at this pore size distribution, we find out the NIMR transverse relaxation, the T2 relaxation, is associated with the pore size R, and the complex conductivity, which is a method maybe some of you are familiar with, and definitely Professor Astra is very familiar with this, and she's expert in this. So for this SIP relaxation time, we can also correlate it with our diffusion coefficient, as well as the tau, which is the relaxation time of the SIP, which you can get from the SIP signal. And they both are sensitive to this pore size. So we can do a joint inversion of these two data together. And this is the work we published in 2017 on GGI, and we demonstrate this workflow, how to combine these two data sets together to jointly invert this R to get a better, more robust estimation of this pore size distribution. And we apply the same kind of concept on this carbonate rocks, which is this specific rock is a oolitic greenstone from the Abaco Formation, and this one we basically show that the joint inversion is very much linked towards the NIMR results. And from this one, we argue that the current SIP modeling framework didn't really consider some other mechanism, but I can talk about this in a completely separate talk. But we're working on this paper and trying to publish this data sets. So another very interesting parameter we always wanted to get, basically the holy grail, is the hydraulic conductivity. So the idea of calculating the hydraulic conductivity is usually to link the hydraulic conductivity or the permeability K to some sort of this porosity relationship, and very often with exponential exponential coefficient, and then to link with a different type of data, such as NIMR data or the SIP data or some other kind of data. So for the SIP per se, we basically have two types of K estimation models. And the first model is called the merokarst TC model, and this one using the cutoff time to basically divide the free fluid from the bounded water, and basically considers this free fluid is the one only the one component contributed to the hydraulic conductivity. And another type of this estimation model is called SDR model. It's also very popular used in estimating permeability from the NIMR signals. And in this SDR model, you also have some constant like this C here, A here, and also the B here, but you're using this T2ML value, which is a geometric mean of the T2 spectrum, and to use this as a characteristic value, and also using this porosity information. And here is our trial on the carbonate rocks. I just show you the previous slides to see if this SDR model can predict the permeability compared with our actual air permeability calculation. And you can see this is a one-to-one line, and on the y-axis it's SDR predicts permeability value, and on the x-axis is the actual measured air permeability value. And I would argue such prediction is within the acceptable range for the K estimation. At least most of them are within an order of magnitude of the misfit. So the next one I want to introduce is how we process or use the borehole NIMR information. Here is an example from our Kansas Abaco Formation, and this is an effort doing the CO2 sequestration into this deep formation, which is about 5,000 feet deep, and trying to sequester the CO2 into this into this formation. And during this process, they did some borehole NIMR measurements. And this borehole NIMR measurements, as this one, as the left one showed, it actually has this the T1 relaxation, which on the right, and in the middle has the T2 relaxation. And then you can see the color, the heat map showing the porosity distribution, and the warmer the color gets, the higher the porosity. So you can note that this NIMR relaxation time, they're not continuously, they're divided into the bins. And this is because of the fashion out of the way the borehole NIMR works for this type of oil and the gas NIMR application. And some of this you probably can also say are not fully decayed, especially for this T1 relaxation time. And if we do a comparison between the log NIMR and also the col NIMR we took from exactly the same depths, you can see the log NIMR is labeled in black dots, and the col NIMR is in the red dots. You can see they're basically they still have a significant difference between these two. And some of them are pretty well to capture the trend of each other, and in terms of the change in porosity, but the magnitude of the porosity always has some difference. So you're probably wondering, besides T1 or T2, besides the porosity and the pore distribution, what other information we can get? So this is a good example to show that why we care some other information. What other things that NIMR signals can tell us? So this one showing that our effort on processing this borehole data, trying to get the T1, T2 ratio. So the T1, T2 ratio has been interpreted as the indicator of the molecular environment of the hydrogen proton. Both T1 and T2 are controlled by the surface relaxivity, which depends on the mineralogy as well as the surface physical chemical properties. When the T1, T2 ratio equals 1, that means basically in a bulk and unrestricted space. And when you have a water interact with the solid surface, you are expecting this ratio to exist 1. And this T1, T2 correlation can be simplified using this equation here. You probably say this is a lot of parameters within this, but essentially this T1, T2 ratio is really depending on this two parameter, which is tau m and tau s. This tau m is a surface diffusion correlation that describes how long the molecular jumps between the absorbed molecules. For example, if you have the water molecules in which diffuse across the pore space. And this tau s is called a surface residence time, and this describes the time period of the water molecule staying on the pore surface. So from this, you can see that the T1, T2 ratio is actually a characteristic parameter for the molecular mobility. And in this effort, on the left, we're showing the T1, T2 ratio for 5 different type of complex samples. And in the maps, the first one, the A is a mudstone, and we have the packed stone. B, C is a greenstone, D is a breccia, and it's an incipient breccia, and the E is a breccia. And we argue that the T1, T2 ratio is actually can be used as an indicator to differentiate the different lithology. And we apply the same kind of idea in in some other study, and this is a very recent work my other PhD students are doing right now, and she's in the process of wrapping up this work. And in this experiment, she prepared a lot of this clay sediment samples, and by varying the water saturation degree, in this case, we use the relative humidity as an indicator from 11% all the way to 100%. We measure the T2 relaxation time at different stages. We also measure the T1, T2 mapping of the different saturation degrees for this clay sample. And here I show one of the example, which is a Denver bentonite, which is a calcium smectite. And you can see this as we increase the RH, which is the relative humidity or the saturation degree, and we can also see both the shifts of the T2 relaxation time, as well as the difference in the T1 T2 ratio. So this black dashed all the black dashed rectangular here are corresponding to what we argue is the hydrogen bonded water. You can call that those are the interlayered pores, where the water is tightly bonded as a hydration layer in the clay sediments. However, this red spots, as the red rectangular highlighted here, we argue that it indicates the water has been absorbed in the interparticle pores, and this is our illustration showing. So we argue this black one is the internal clay layer and a hydrated layer, and the red one indicates the interparticle water based on all this previous analysis together with the T2 spectral analysis. So this is just one of the examples how we can use the T1, T2 mapping. Then I want to take you to a current work we're working in the field and trying to study this merokarst system. And this is a picture I show at the beginning of my slides. And this is the Flint Hill, Kansas, which is a tall grass prairie. The field component of this work has been recently published in this paper. And we have some subsequential lab analysis and also the modeling work we're currently working on, and this is work has been in the revision right now. So let me introduce you a little bit of this merokarst system. So what is a merokarst and why we want to study the merokarst? Merokarst system, which is different from this holocast system, the merokarst is featured by the thin and the interbedded limestone and the shale layers. It's an incomplete karst system, which means you are not expecting the sinkholes or cave developed in such a merokarst system. So the thickness for such each lithologic formation is quite thin, usually about 1 meter to tens of meters, and the entire system is usually very shallow and has a very high percentage impurity. So you don't expect a pure limestone or pure dolomite in this kind of formation. And this kind of a merokarst system can develop some level of fracture and also conduits. And the flow direction for this kind of system has been traditionally argued to be mostly horizontal, but actually our work showed the vertical flow path is also very significant in this system. And the CO2 content is really high, which is the CO2 from the soil. So in this system, especially in this particular field, we really care about this lithological heterogeneity, the fluxes of water, sediments, carbon, and nutrients, the weathering and the landscape evolution, as well as the reaction to the perturbation. And we're trying to answer some of these particular questions, such as how is this vertical connectivity versus horizontal connectivity? And can we quantify the water flux and storage? how is the water residence time in the different layers? And also the last question is, what is the weathering pattern and the rate? Can we predict this? So to summarize our current effort, we're trying to answer the first question by not only doing the fieldwork, but also doing some surface LMR simulation. And the second and the third question is the one I'm going to talk about today, which we're going to use the field study as well as the lab study to answer this large-scale water flux and storage, as well as a small-scale water residence time during the drying process. And then lastly, it's to answer this weathering pattern and rate question, two of my students are actively working on this. One is doing a lab-controlled experiment on the calcite precipitation and the dissolution, and another one doing the numerical simulation using LBM and coupled with free QC to look at the reactive transport modeling during this weathering process. So let me take you to this concept research site. As I mentioned, this one is a tall grass prairie, has a low disturbance and a very rich research infrastructure, over 35 groundwater wells for the groundwater level composition and temperature monitoring, and has been collect this hydroclimate data for the past at least for the past 3 decades. And the two limestone formations were focused on the ice limestone formation as well as moraine formation, because these two are the main aquifer in this region. And you can see from this figure on the lower left corner, this one showing this small watershed here, and all the dots showing the monitoring well, and this blue line showing the intimate stream here. And this one showing the carbonate bench exposed on the surface. So what kind of geophysical measurement we did? So we went out during the dry season, and we did 7 surface NIMR soundings, 6 borehole NIMR tests, 6 ERT profiles, as well as 8 GPR profiles. And we designed our survey trying to capture the spatial pattern from the upslope to mid-slope to the valley, to look at the morphology control on the water distribution, as well as to look at the stream impact, to look at the surface water groundwater interaction. So along this near the stream outlet and also on the upstream, to look at this water distribution along the stream. I'm not going to the detail of all this data we collect from this site. I only want to showcase the surface NMR data here. So if you can see, the surface NMR is all this red diamonds indicates, and we collect at 7 different locations, which covers the upslope, mid-slope, as well as the valley. And from the surface NMR data, we can have a good understanding of the water content at different locations. We see the low water content values in the up and mid slope locations, and we also observe the highest water content in this S7 data in this Neva limestone formation, which is well below our target formation. And this increased. We also see increased water content in all surface near the shallowest limestone shale boundaries. And however, due to this long dead time of the surface NMR, which is 10 milliseconds, that means any water can relax less than 10 milliseconds cannot be detected using this surface NMR setup. That means we underestimate water content systematically. So the borehole NMR is also borehole NMR data also reveals some very interesting pattern. For this borehole NMR here, this 6 dots showing here. We have all those wells from at different locations. Since we have to deploy this NMR tools in the well bowl, so how deep the borehole IMR can go, it depends on the depth of the wells. And the interval of the borehole IMR for our particular study is 25 centimeters. And here I show these two wells. One is 4-6, which is this one here. And another one is well 1-6, which is this well here. So one is upstream and one is downstream. So we can see the water content relaxation time as well as the T2 ml being labeled on these two figures. And we can see the shale layer has a high water content and some of the small pores. We also observe the bimodal distribution of the water in the limestone layers. And we also observe more mobile water in the upstream direction in this well 4-6. And we can also observe very good, a great vertical connectivity from this well bone here. So if we compare the surface NIMR with the borehole NIMR, the penetration depth of the surface NIMR is not limited by the depth of your well bone. It's basically limited by how large you set up your loop. The resolution of surface NIMR, however, can be suffered by different factors, especially especially comparing to the borehole IMR. Usually the surface IMR has a lower resolution than the borehole IMR, and the dead time for the surface IMR also significantly longer than the borehole IMR. And for in terms of the fashion of the measurement, the surface NMR, you just need to lay your cables on the surface, and for the borehole NMR, you do the measurements, deploy your probe into the well. I want to point it out. This is the top 5 to 10 meters of the data showed here on the surface NMR sounding. They're subject to the high noise level at all of these surface NMR locations due to some possible interference from some of the nearby EM noise. And due to this long dead time, compares the water content between these two, this surface NMR definitely underestimated the water content. And this comparison gave us a hint that how we can wisely design our geophysical survey with full consideration of the area of coverage, the resolution, the limitation, and also some other logistic considerations. And currently we're working on simulate the response of the surface NMR under this 10 milliseconds dead time, and then trying to somehow to synthesize part of this missing data to make up the part of the signals which cannot be recorded using this setup here. So the last part of this is some of the lab work, which is a continuous effort from this field work. I'm not sure if you have heard this term called the rock moisture, which means the exchangeable water stored in the weather bedrock beneath the soil. And this rock moisture is really important in regulating the groundwater recharge and discharge, and also important in supplying the water to the ecosystem. And this part of this rock moisture, however, are not very well understood. The quantification of the rock moisture partitioning, we don't know that, or we don't know the evolution of the seasonal change of such rock moisture partitioning. So with this question mark in mind, we designed our experiment following this concept field work. And we took some core samples from the ice formation as well as the Morel limestone formation, and also sample from the shale formation, and we're trying to use the lab experiment during a drainage experiment to look how the water can be shifted as during the dry season, as it drying through, and how the water distribution can be altered during this process. So we first took out of sample and we put into this, we made some thin section out of this and trying to look at the mineralogy of these different samples. And just some of the quick observation. The E2, which is limestone, the ice limestone sample, we see some visible well-connected pores, and for the lower part of that, however, we don't see some of the visible porosity. And for the Morel limestone, which is the one on the left, showing this M2, and this one showing the isolated pores filled with some cement. So from the thin section, at least we can see from that particular sample, the connectivity of those pores in the M2 sample are really poor. So then we're doing some, we designed the experiment, we fully saturated those samples, and then we put them into a climate chamber to control the drying process. And we measure this entire drying process from fully saturated until fully dried. And the time interval is varies from a few minutes to 30 minutes or so. And this is just a picture showing that the drying after 15 minutes, and the drying after 30 minutes, and drying after 120 minutes for one of this sample. And so this is the drying rate for the different samples labeled as E2, E7, S1, and M2. Just to remind you again, E2 and 7 are the ice limestone, which are on the top of this on the top near to the surface, and then we have the shell layer, which is in between the ice layer and the Morel layer, and the M2 indicates the lower limestone formation. And you can see the samples experience the different drying speed and also have a different drying period. And for the drying experiment, here I summarize what we have done using the NMR. So after at each of this drying sampling time period, we took the sample out and we performed the T2 relaxation time measurement, and we record the porosity, water content, as well as the T2 distribution. And we also use some of our recent developed multi-Gaussian analysis method to decompose the peak to calculate the composition of each individual peak to the T2 relaxation. So and also for some of the sample, we also measure the T2 experiments to quantify if there's any coupling of the different pore size in the system. So I give you a quick overview of the peak decomposition method. So this is on the left, this is the regular T2 relaxation spectrum you can expect. And the current way to analyze the T2 relaxation time is usually very arbitrary and not very quantitative. So we develop a multi-Gaussian fitting regime to automatically peak this characteristic peaks, and also to calculate the contribution of the different peak to the overall shape and of this spectrum. So using this method, we get to analyze our T2 relaxation curve in a more quantitative way. And this one showing here, we have a fully saturated we'll have a fully saturated condition, which is the left column, and we have a half saturated condition, which is the middle column. And you can see how this peak shows and how this peak decomposition results reviewed. And if we look at this one, so the different rock from E2, E7 to S1, S to M, their drying pattern is different. This is only can be reviewed by such peak decomposition method. When I talk about this drying pattern is different, when I meant that, for example, in this E2 rock, the first peak disappear, and then the peak 3, the largest peak first disappear, and then the second largest one, and then the blue one and then the red one. However, for some other rocks, such as this rock M here, all this peak, they disappear simultaneously. That means the water actually withdraw from all the pore sites simultaneously. And I think this is a really interesting finding and can tell us a lot about how this water redistributed in a pore environment in different type of rocks during a drying season. And this gives us a hint to calculate your entire water budget to understand how much of the free water, meaning the high peak water, can be freely flow to the stream, and how much of this water, meaning all of those bounded water, like this peak 1 shown here, the small peak, are being reserved and maybe can possibly used by the vegetation roots. So the next one, we also did this T2 measurements for some of the samples. And here I only show one example here, which is the sample E2 at the saturation 50%. And the measurement calculate for the storage time of 100 milliseconds. And you can see this, to give you a little bit background of the T2 measurement, this measurement is designed to detect any chemical shift of a proton and monitor the exchange of the water among different pore environments. So such experiment consists of two T2 experiment periods with a short storage time in between, which allow the water molecule to exchange from one pore environment to another one. So if we have a long storage time, that means that would allow the molecule in a large pores to exchange. So when we analyze the T2 results, the pore coupling, when we can see there's evidence of the pore coupling, this is evidenced by any of this off-diagonal signals. If all the signal is along the diagonal of this T2 map, it suggests there's no exchange among the water molecule in different pores. However, if we have any of this signal, like these two rectangular highlights here, which are off-diagonal signals, that means we have this we have the water exchange in a different pore system. So I think wow, I just want to wrap up here to tell you a little bit my future plan. And obviously, I haven't fully answered all this question yet, and there's still a lot of unknowns left, which needs a lot of research to be invested on that. So for me, I think I'm probably gonna go back to the field more and to do some of the more of this seasonal change time-lapse experiments, and also to look at the water and the nutrients flux, and also to design experiment to investigate the interaction of this groundwater with the stream and the CO2 the CO2 concentration. Also to look at the porosity and the permeability evolution during the weathering process. And in terms of NIMR, I really hope my work in the future can be focused on improved NIMR, surface NIMR, borehole NIMR data analysis by incorporating some of the lab NIMR data. So essentially to link the NIMR from the different scales, and also in the future, if we have the opportunity to do some of the 3D NIMR experiments in the field. So with that, I want to thank the Council Prairie, LTER, and also thank Kansas, University of Kansas for the staff and the GRI fund, and also some of the other travel grant to my student. And if you're interested in my research topic, you're welcome to email me and also to follow me on Twitter. And thank you for the invitation. Thanks.
Thank you, Dr. Chi. It was a very, very interesting presentation. Professor Ricardo and Professor Andrea, do you have any considerations?
I just wanted to to thank Chi for giving us this inspiring presentation. And let's see the questions from YouTube, and then we can go on discussing.
So there is a question from Giovanni Moreira. He's a colleague from our lab, and he asks if any of these experiments have been performed in boreholes.
Yeah.
Borehole experiments.
Yes. I'm sorry, I probably was not very clear, but our work, but this work and this work, they are completely borehole application. And here we are using the Halliburton borehole NIMR tools. This two work, and also we apply near surface borehole tools, which is the DART system from Vista Clara, and using 25 to 50 centimeters, it's a centimeter interval to look at this water distribution in the merokarst system. Yes, so we have borehole experiments and the borehole data.
Thank you.
And from different type of borehole system. So this one is a shallow surface application. So the borehole is the borehole to the probe is much smaller, and this one here is the Halliburton borehole tool, which we rented to deploy at this particular site. And you can see the depth is from 4,900 feet to 5,000 feet. And so I only show like 100 feet interval here. But this borehole tool, the traditional oil gas borehole tool. So we also experience the difference, the cons and pros from different type of borehole tools. I'm saying this YouTube comments here. I think Giovanni is trying to ask me water flux in the wells. Yeah, this is a good point, but as I mentioned early on, when we measure that, we have a very dry condition, and we did not expect this water flux in the well during the time when we measured, because the entire measurement time is probably about 1 hour or so for each of this borehole. So we didn't really interact with this actual dynamic flux situation when we did this experiment.
And Professor Andrea also asks if you could talk a little bit more about the 3D NMR.
Yeah, actually 3D NMR work has been done by a lot of other groups. For example, the Leipzig groups from Germany, and also another group from Jilin University from China. And there's some data showing they just do this 3D acquisition, and also of course you have to develop the 3D inversion for the surface NMR. And let me show if I have some of this. So yeah, maybe this one can give you a little bit idea. So this is.
I think
yes.
you need to share your screen with us.
Oh, you cannot see my screen?
No.
Oh.
Okay.
So thank you. Yeah, I was talking about this all the time. I saw that you saw that. Okay. Yeah, thank you for the reminder. Yeah, so this one here is actually showing some of this surface NMR, how we actually measure surface NMR. You basically have a transmitter and also receiver. And for us, we're using the same loop. And there's a different way you can set up your loop and different shape, and you can determine the best configuration for your best interest, considering the noise level and also considering some other depth of penetration and so on. And this is one example in this review paper by Bin Rumzet in 2015, and this is another one on the bottom showing this actually showing this 2D surface NMR inversion. But there's already some work has been done doing this 3D surface NMR work, and not just the theoretical synthetic data, but also some field data as well. So Andrea, is that 3D work you are referring to?
Yes, thanks.
Oh, thank you. Yeah.
Chi, may I ask you something? You presented us with the very, very nice case study on the variation of water table, how this responds to porosity in petrophysics, and how this is interesting for the understanding of the response of this merokarstic system to changes in climate and environment. But do you have anyone working on the biological side of this problem?
Wow, wonderful question. Can anyone still see my screen?
Yes.
Yeah. So when we, so it's not in presentation mode, but can anyone see it?
Yes.
Okay, great. Thank you. So actually, in order to answer that question, so if you see this one here, we're talking about this rock moisture with this idea of how much water is actually available in this unsaturated weather rock for the vegetation to take. So this is a huge question mark about the ecological control. And especially this type of control is important for the carbonate terrain because of a lot of work has demonstrated such ecological drill is a very important force for this landscape revolution, and also to facilitate ending of this castification process, like precipitation and dissolution. But so far, not really. I think I'm hoping that I can collaborate with someone to look at some biological components. But currently, we're also trying to understand for this very top surface of the soil, and we're trying to understand how much of this bacterial community within this top soil can impact this CO2 flux, and therefore impact the weathering pattern. I'm teaming up with someone else in Kansas and trying to answer this question.
That's very interesting. In fact, for another very different reason, we are collaborating with another group working on the karstification.
Yeah.
Very it's different because this is a merokarst, and in their case is a huge karst system, and they are linked. They are linking the biological function, especially vegetation on top of the karst, and also inside the karst in the valleys that were uncovered because of the fall of the roof of those karsts, forming very long valleys. So they are trying to understand how the vegetation works on those different environments. But I don't think they are looking at this at the perspective of the critical zone. That is completely different, because then you're trying to understand the whole budget of nutrients and water inside the soil.
Yeah, that's very interesting, because I know recently I've been attending some seminars. So one of the researchers actually brought this up, that in order to fully understand, to model any of this castification process, so you need to consider this vegetation impact, which mainly coming from two things. One is this this canopy, the basically evapotranspiration, and also one is actually from the root. So like how much is the water and this root respiration, and also the decomposition. And sometimes you can even link that to, for example, the wildfire and the after fire, or prior to fire or after fire. And actually our particular location here in Kansas, this watershed, we also have prescribed fire every 4 years. This is what this FALL stands for. This FALL means every 4 years we have prescribed fire here. So it will be also very interesting to investigate here. But here is all tall grass prairie. We don't have very large trees with a large canopy or very deep roots. So the entire ecological function is going to be quite different. I think it's also highly depending on the species.
That's great. Something else I would like to ask is that, are you
Yeah.
sampling the water from time to time?
Sorry?
Are you sampling the water from time to
Yes.
time?
Yes, we are. It's just not it's just not my job, so I did not showcase here. So we have very intensive water chemistry data actually, including the temperature, CO2 concentration, nitrogen concentration, and also some other major ions concentration.
And carbon isotopes. Did you do that?
Yes, I believe they have this. I believe they have this data, but I don't think we've been considering in our current framework when we explain the lithology and the flow path. But we're definitely going to investigate in the future. Yeah.
Thank you very much. Thanks a lot. Very nice talk.
Thank you.
Work.
Dr. Chi, may I ask you a question as well?
Sure. Yeah.
So let's say that in the pore, there are some impurities like any magnetic mineral, ferromagnetic mineral. How the presence of ferromagnetic mineral can affect the NMR acquisition in field?
It is a very good question. So any magnetic material definitely have impact on this mineralization, on this magnetization process. So if you can see this one here, so basically when we say that this diffusion term, the T2D here, the diffusion relaxation time is also coming from the inhomogeneity of the magnetic field. So if you have some existence of, for example, like paramagnetic minerals, and it's definitely going to impact your signal. There's some research done by some other people like Keating's paper in 2007 in Geophysics actually investigated, for example, the as a hematite and with a different type of coding, how this going to impact the NMR signal. The simple answer is yes, it's definitely going to have an impact because it's especially when you have this paramagnetic material.
Thank you.
And for a lot of our study, I haven't shown this results here. For most of our study, we also do the XRD measurements, so we know the mineralogy. So we are relatively confident of what we have in the system, and then in order to isolate any of this impact, such as from paramagnetic material.
Thank you. Thank you for answering. There are a few more questions. First, Giovanni again asked if you could go 4D NMR, and you were talking about the presence of bacteria. So he asks about magnetostatic bacteria.
Okay, yeah, actually I saw the Giovanni's question. Actually, the first one he was asking what's a main flux medium. So actually, could you clarify? Well, what do you mean by the main flux medium? And the second question is how the different signals decays differently. Yeah, so I assume you're referring to this drying process. This drying process experiment is a work we just submitted being under review. And this drying process, with the help of this peak decomposition method, we actually can really tell, just a second. We can actually tell that how the signal from the different peaks actually change during these experiments. And 4D NMR, 4D, I'm assuming you're considering the time as another dimension. So the 4D NMR, I think, yes, if you do a time-lapse experiment, yeah, of course you can get some of time-dependent measurement if you do just like you do any other kind of NMR geophysical experiments. So as I just answered as I just answered Andrea about the current 3D surface NMR application and the practice, there's a possibility you can add the time dimension to that by collecting the time-lapse data. No, we haven't done any bacterial experiments on this one. I'll investigate any role of this a magnetic tonic bacteria, unfortunately. Yeah, but this is a good point. Letitia was asking, any idea of possible difference between the nuclear magnetic resonance data obtained in the field and lab? That's a great question. Yes, a lot of difference. We are actually working on that to demonstrate the difference. Here, I only show you the difference between the surface NMR and the borehole NMR, and I already demonstrated there's a lot of difference between these two type of method when we apply both on the field. But also, there's a significant difference between the lab NMR and also the field one. One of the example I showed earlier is this borehole NMR data compare with the lab NMR. You can see the difference is huge, I would say. And the most of the time, this log NMR even cannot fully decay due to the time measurement limitation. Not only about this, but also in terms of if you look at this table, in terms of this dead time and the measurement condition, they're all different. And for the lab NMR, usually the dead time is much smaller than this. So that means you can actually capture more of this water from smaller pores. And the measurement, of course, you need to do the call plugs. You need to cut your plugs and load into your NMR machine. I'm not sure if I fully answered this question. And the iron reduction. Yeah, I haven't done any of this experiment yet, but I think it will be very interesting.
Thank you, Dr. Chi. Any other questions, guys?
No, just that to thank Chi for being with us, and it was really great to have that perspective on the critical zone in here, and we are really not into surface NMR. So having seen these results is really interesting to try to understand and try to think about using this as a technique to monitor the water table. Thanks a lot.
Thank you,
from
Professor.
Collaboration perspective, right, Chi?
Yes, definitely. I'm looking forward to visiting Brazil someday. Yeah.
It will be great.
Yeah. So I feel this is actually my first Google presentation, and I feel like it's definitely not as interactive as the face-to-face. So I might not be very clear about some of the things. And if you have any question, I just want to chat with me on the research, you're always very welcome to send me email or just message me. And I'll be happy to chat every single aspect of this research. And I'll be very happy to show more data or discuss of the topics with you.
Thank you very much.
Thank you. Yeah.
Thank you. Thank you for your presence again, Dr. Chi.
Thank you, Chi. And
Thank
sorry
you.
for delay. And I'm learning English, so it's difficult. But
No worries. Thank you.
But thank you for the excellent presentation. And your research is very interesting. And thank you.
Thank you. Thank you, Lucia. Thank you, Andrea. Thank you, Ricardo.
Yes, it was really inspiring, and I think you're doing some really interesting work. Yes, I was not aware of the last ones. I have seen the latest, let's say, things that have been published, but you were going very interesting directions and interpreting everything together. So I think this is very interesting, and I hope we can collaborate. So here we are more into the bacteria and maybe the iron that you can see, and that's I think we can collaborate with you and see maybe in the future have some surface NMR here and to study some aspects of the critical zone here. I don't know. I think we need to find some questions here and some good observatory to place this research. But
you have Amazon there, so
yes, exactly.
no
yes.
worry about it.
Yeah, we do. Yes. I think we should be putting this together and make this effort.
Yes. May I ask you a final question? Just to, do you have any special reason why you have chosen those merokarst places? Because is it because of the heterogeneity of the lithology? Or,
this is actually one reason, and another reason I feel like if you've been any of this traditional karst community, they all study very deep, mature, well-developed karst system, which means the sinkholes, the caves, and so on. And they have specific system of the modeling approach and to characterize the flow paths and so on. However, such very thin interchanged limestone shell, this kind of system is very widely available anywhere in the world. For example, the one I showed earlier was one of this example in China, in Guizhou province, and we have here in the mid-continent US, and we also have a lot of other places in Europe. I haven't checked in Brazil. Maybe you also have some of this system there. And another reason is we believe this is early stage of classification process. So understanding this early stage will help us to understand the future and to really come up with a modeling, at least conceptually, how this future classification process is going to develop. And also the third is just for logistic reason. I'm very close to this place, and this is also very important, the local groundwater supply for that region. I think this is very important. Yeah.
Okay. But it's very interesting. We have some geological situations in Brazil that are not that different from there in terms of those kinds of layerings between carbonate and shale.
Yeah.
But we have also some places that are much more karstified than those.
Yeah.
So there are several different possibilities for like having a similar site, but in a completely different climate.
Mm-hmm.
Right, exactly. To look at the climate gradient must be a very interesting one. But here we have a very gentle, mild climate gradient, and only because we study the site meaning that we don't have really a stretch of gradient to look at. So we only have this one particular setting, but with enriched precipitation and vegetation, I assume a lot of things going to be different. And even just within the limestone formations, we often see also from this study, the formation, the weathering pattern is very different along this vertical profile. And it's really interesting just to think how a drop of water getting into the ground from the soil, getting into the weather, the bedrock, and then go to down. So it's just essentially we're trying to understand this process.
Yes.
Great. Thank you very much.
Thank you. Thanks a lot, everyone. Thank you.
Thank you. See you.
Have a good weekend. Bye.
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 Thank you, Xi.